Okay, so let's finish this section on the second derivative test. Okay, we'll do this function cosine x squared, but we're only going to look from 0 to pi. So the closed interval from 0 to pi. Okay, so you can take the first derivative of this and you'll get minus 2x sine of x squared. Okay, so the first derivative is actually going to give me the critical numbers. So the critical numbers of this can be found by setting minus 2x equal to 0 or sine of x squared equal to 0. Well, for sine to be 0, the argument would have to be either 0, pi, or 2 pi. So x squared has to be equal to 0, pi, or 2 pi. So that would mean x would have to be either 0, square root of pi, square root of 2 pi, or square root of 3 pi. Okay, well, fortunately, let's see. We'll see in a minute if all of these are actually in this interval. So we'll have to check that in a minute. So and here we got 0 as well. So 0 is actually a critical number from both of these equations. Okay, so now let's get the second derivative. Now I use the product rule to get the second derivative. So here is the second derivative. All right. Now let's test 0 here. Well, if we plug 0 into the second derivative, we get a 0 here, and we get sine of 0, so we're going to get 0. So darn it, the test failed. Okay, it failed. But x equals 0 is an endpoint just to the right. So I'm not sure what that's saying, but x equals 0 is an endpoint, so to the right. So actually, oh, I know what I was saying. So if you look just to the right, should have put a comma there. It's an endpoint. Okay. And just to the right of x equals 0, the function is decreasing. So technically, f of 0 would be an endpoint relative max. And I'll explain that when I show you the graph. Okay, now for square root of pi, I'll let you do the math. I had to use a calculator. So when I plugged square root of pi into the second derivative up here, I ended up getting 4 pi. And 4 pi is a positive number, so that means that f of square root of pi must be a relative min. Okay, now let's do square root of 2 pi. Well, square root of 2 pi would be, let's see, square root of 2 pi, when I plugged that in, I actually got negative 8 pi. So I got a negative number when I plugged that into the second derivative. So f of square root of 2 pi is a relative max. And then square root of 3 pi, when I plug square root of 3 pi in, I got, let's see, what did I get here? Square root of 3 pi, I got a positive number. So when I plug that in the second derivative, f of square root of 3 pi is a relative min. And actually, let's see, yeah, that's fine. So square root of 3 pi is less than pi, technically. So it does fall within the interval. Okay, so now let's take a look at what we know. We know we get a minimum at square root of pi, which is roughly this value, and we get a minimum at square root of 3 pi, which is roughly this value. Okay, and then at square root of 2 pi, we get a maximum, which is this value. So there's your maximum, there's your relative max, and then here's your two relative min. Now, the point 0, 1 is a maximum because, as I said, just to the right of 0, the function is decreasing. So in this neighborhood, that point is a maximum because, remember, we don't actually count the stuff on this side. All right. Now also, this point right here at what was it? Let's see, pi. Okay, so also the point at pi, that's also an endpoint relative maximum. So these are actually considered endpoint extrema because they're the endpoints of the interval and they're the largest values in their neighborhood. So anyway, you can see that the second derivative test might not be the best test to use on complicated functions because finding the derivatives are a little bit difficult. So you might have want to go back to the first derivative test for this problem. But I always like to show students an example of a complicated problem, one that's complicated to get the second derivative, so they can see that you really are better off if you use the second derivative test only with polynomial functions, and then on most other functions use the first derivative test, unless of course your teacher makes you use the second derivative test. Okay, let's do another one here. This function, the first derivative is 8 cubed minus 8, and if you set that equal to 0, you get a critical number of x equal 1. The second derivative is 24x squared. Well, I only got one critical number to check, and that's 1. So I'm going to plug 1 into the second derivative. I'm going to check and see if I get a positive or negative number. So I got a positive number. Well, since the second derivative is positive, then f of 1, which is negative 3, because if you plug 1 back into this, you'll get negative 3. So that's going to be a relative minimum. And you can see that's actually going to be right there. And notice that if you look here, you'll see that the graph is concave up. That's why the second derivative was positive at x equal 1. So this point here is the point 1, negative 3, and that's your relative minimum. Okay, here's another one. Let's see, on this one, the first derivative was 4x cubed minus 12x, and then when I factor 4x out, I get 4x times x squared minus 3. And if you set that equal to 0 to get your critical numbers, you'll get x equals 0, x equals square root of 3, x equals minus square root of 3. Well, then you get the second derivative, which is 12x squared minus 12. And notice that if you evaluate the second derivative at 0, you get a negative. So f of 0, which actually is 0, is a relative max. So here, you know, the 0, 0 point, we get a relative max. All right? And then if you check it at square root of 3, when you plug square root of 3 into the second derivative, you actually get a positive number. So f of square root of 3, which is negative 9, is actually going to give us a relative min. So that corresponds to this point here. So that's square root of 3, and what's the y value? Negative 9. Okay, and also the minus square root of 3 does the same thing. If you plug minus square root of 3 into the second derivative, you get a positive number. So that point minus square root of 3, negative 9, is also a relative minimum. And again, that's just using the second derivative test. Now again, here's another one that might be difficult to use the second derivative test on because of the difficulty in finding the derivative. But I went ahead and did it. The first derivative you can get using the quotient rule, and then you can apply the quotient rule again and get the second derivative. Okay? Well, from the first derivative, I only got one critical number, and that's x equals 0. And then when I plug 0 into the second derivative, I got a negative value. So that tells me f of 0, which is actually 4. If you plug 0 back in here, you get 4, is a relative max. So you can see the picture over here, and you can see that the point 0, 4 is indeed a relative max. Okay? Okay. One more application here. The point of diminishing returns is actually a point, like a function might be increasing, but then the rate of increase begins to slow down. Well, that's generally called a point of diminishing return. I was trying to find one of these pictures I could show you to show you that. See, this graph is increasing, but right here it's still increasing. But the rate of increase is slowing down because it's concave down. See, over here when it was increasing, it was concave up, and now it switched to concave down. So the rate that it's increasing actually is slowing down. And so, in other words, the second derivative there is actually negative. So going back to this problem, to find the point of diminishing returns, what I need to do is find the second derivative of this revenue function. So here is a revenue function, and then if you find the first derivative, which I'm sure you can do this, you can find the derivatives on your own here. But the first derivative is minus 3 over 20,000 times x squared minus 300x. And then the second derivative actually is minus 3 over 10,000 times x minus 150. Okay, so basically what we're looking for here is we're looking for the point of inflection. So we set this equal to 0, and we get x equal 150. And if you actually check this function just to the right of 150, you'll find that this function is concave up, and just to the left of 150 you'll find that the function is concave down. So therefore, when x equal 150 or 150,000, that's the point of diminishing returns. In other words, the returns on your revenue begin to slow down as the revenue is still increasing, but it's increasing at a slower rate than it was before. And so a good example of this is if you're tracking a stock and the stock is increasing, but all of a sudden you notice the curvature change. So maybe right here it switched from concave up to concave down. Well, that would be a point of diminishing returns, but that might trigger you to sell somewhere in here, because think about if it continues this path, you know what's going to happen. It's actually going to continue to go down, and obviously you want to sell before the value of the stock starts dropping. So that's pretty much it on concavity and points of inflection. And so we'll look at some other topics on the next video.